Hello, in this lecture we answer two questions. In the first question we find out the area of this pentagon ABCDE, and in the second question we find out the area of this green shape. So we start with the first question. In the drawing we have pentagon ABCDE. So what is a pentagon? A pentagon is a flat closed shape with 5 sides and 5 interior angles. This is pentagon ABCD. It has 5 sides, 1, 2, 3, 4, 5, and 5 interior angles. 1, 2, 3, 4, 5. So, in the drawing, we have pentagon ABCDE. We know that ED equals to 1, BC equals to 1, and EA also equals to 1, AB equals to 1 minus x, and BC equals to x. This is right angle EDC is right angle. This is angle EAB. This is also right angle. Again, our task is to find out the area of this pentagon ABCDE. So first of all, we join points C and C together by a straight line. And we join points E and B together by a straight line. In the next step, we extend side VA by straight line in such a way that the extended part will be equal to x units in its length. We define this point as point M. So AM, the extended side, is equal to x units in its length according to our construction. We know that when you extend the straight line by straight line, the result is a straight line. We extended the straight line BA by straight line, so the result BM is also a straight line. So if we focus on the upper side of the straight line BM at point A, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. For which angles we have at the upper side of MB, the straight line MB at point A, we have this angle that is the right angle, plus this missing angle, in total must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points E and M together by a straight line. By joining points E and M, we can enter there the right triangle EAM. So in the next step, we will prove that this right triangle EAM can go into this right triangle EDC according to side angle side rule. So we copy those two right triangles in an equation. We prove that they can go into each other according to side angle side rule. Okay, those are the two right triangles that I copied from the original drawing. This is the right triangle CEAM and this is the right triangle EDC. So what those two right triangles can go into each other? First of all, MA equals to CM equals to X. They are both equal to X and therefore they are equal to each other. Side MA of the right triangle MEA equals to side CD of the right triangle ECD. They are both equal to X and therefore they are equal to each other. MA equals to CD equals to X. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So this is angle CAM. This is equals to this angle that is actually angle EDC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides they are both equal to 1 and therefore they are equal to each other. EA equals to ED equals to 1. So side EA or that EAM equals to side ED or that ECD, they are both equal to 1 and therefore they are equal to each other. So if you prove that those two right triangles can go into each other according to side against side rule. That is to say, if you prove that those two sides and the angle that is included between those two sides, this right triangle ECD are correspondingly equal to those two sides and the angle that is included between those two sides, and the right triangle EAM. And therefore those two right triangles can go into each other according to side against side rule. So if you want to know that the right triangle EAM congruent, this is the sign of congruent, to the right triangle ECD according to side against side rule. And from the fact that those two right triangles can go into each other, we first of all we derive that they have also the same areas. So this is the right triangle ECD. The right triangle ECD, again right triangle ECD is equal to the area of this right triangle MAE. If we define the area of this triangle as Z, then the area of this triangle must be also equal to Z because they are equal to each other in their areas. In addition, because of the fact that those two triangles can go into each other, we derive that EM equals to EC. EM equals to EC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides, that is to say EM and EC, must be also equal to each other in their layers. If you hold that EM, this side EM, that is equals to side EC. In the next step, we calculate the length of MB. MB equals to MA plus AB. Again, MB equals to MA plus AB. So if you don't, MB total equals to MA plus AB. So MB equals to MA is X, plus AM. AM is 1 minus X. So in total, MB equals to x minus x is 0. So we have to only find MB equals to 1 unit in its length. This is side MB. It equals to 1 unit in its length. In the next step, we'll prove that triangle MEB, this is triangle MEB, convert to triangle BEC according to side rule. So on copy those two triangles in an equation, we'll prove that they convert to each other. MB is actually a common side that belongs to both triangles. It belongs to triangle EBM and it also belongs to triangle EBC. Okay, those are the two triangles that are going from the original drawing. This is triangle EMB, this is triangle EBC. So why those two triangles can go into each other? First of all, we only found out that side EM equals to side EC. Side EM, triangle EMB, is equal to side EC in triangle EBC. In addition, side MB equals to side BC. They are both equal to 1 and therefore they are equal to each other. Side MB in triangle EMB is equal to side BC in triangle EBC. They are both equal to 1 and therefore they are equal to each other. And finally, EB is a common side that belongs to both triangles. This is side EB, this is a common side that belongs to both triangles. It belongs to triangle EBM and it also belongs to triangle EBC. So you know, we found out that EB equals to itself is a common side that belongs to both triangles. So if we prove that all the three sides of this triangle EBM correspond equal to all the three sides of this triangle EBM, and therefore those two triangles can go into each other according to side rule. So if you don't remember that right triangle EMB congruent, this is the sign of congruent. Triangle EMB is not the right triangle, is congruent to triangle EBC according to side, side, side wall. From the fact that they can go into each other, we got that they are also the same areas. That is to say, the outside EMB is equal to the outside EBC. So I do down. The outside EMB equal to the of this line EBC. But what is the outside EMB? There on this side EMB is equal to the base BC times the height AE over 2. And again, there this time EMB equals to the base BC times the height AE over 2. The base, actually the base is MB or BM. And again, there outside EBM equals to the base BM times the height AE over 2. BM equals to 1 times the height AE is also 1 over 2. In total, if you want to do that, the outside EMB equals to 1 times 1 over 2. 1 times 1 is 1 and 1. So in total it is equal to 1 half. If you found out that the outside EMB equals to 1 half. So we can write here that the outside EMB is equal to 1 half. And from this equation 1 half equals to the outside EMB equals to the outside EBC, we know that the outside EBC also equals to 1 half. So the area of triangle EMB plus the area of triangle EBC, in total it will be equal to 1 half plus 1 half, that is 1. Okay. The sum of the areas of those two triangles EMB and EBC is equal to 1 square root in its size. But from the drawing it is very easy to see that the big quadrilateral EMBC consists exactly those two triangles, EMB and EBC. Again, the big quadrilateral EMBC consists exactly those two triangles. And therefore, the area of the big quadrilateral EMBC will be equal to 1 half plus 1 half, that is 1. So if you found out that the area of the big quadrilateral EMBC is equal to 1 square root in its size. And again, the area of the big quadrilateral EMBC equals to 1 square root in its size. But the big quadrilateral EMBC consists the green triangle EMA and quadrilateral EABC. And again, the big quadrilateral EMBC consists of those two shapes, and therefore therefore the sum of the areas of those two shapes must be equal to 1, because the area of quadrilateral EMBC equals to 1. The area of quadrilateral EMBC is equal to the sum of the areas that it consists of. because of the fact that the area of quadrilateral ABC equals 1, it means that the area of this green triangle EMA plus the area of this quadrilateral EABC must be equal to 1. So I have to know, I found out that the area of this right triangle EMA plus the area of this quadrilateral EABCE is equal to the area of quadrilateral EMBC is equal to 1. Okay. The area of the green triangle EMA plus the area of quadrilateral ABCE is equal to 1. But the area of triangle EMA is equal to Z coordinates inside, so we can substitute the area of triangle EMA by Z, and get that Z plus the area of quadrilateral ABCE, in total it is equal to 1. Again, conclusion, we found out that Z plus the area of quadrilateral ABCE equals to 1. Our task is to find out the area of this pentagon ABCDE. So what is the area of pentagon ABCDE? Pentagon ABCDE consists of two shapes. It consists of this white green triangle EDC, and it also consists of quadrilateral ABCE. And therefore, the sum of the areas of the two shapes that pentagon ABCDE consists of will be equal to the area of pentagon ABCDE. So in total, the area of pentagon ABCDE must be equal to the area of the green right triangle EDC plus the area of this quadrilateral ABCE. Repeat again. Pentagon ABCDE consists of two shapes. It consists this right triangle, right green triangle EDC, and it also consists this quadrilateral ABCDE. Therefore, the area of pentagon ABCDE will be equal to the sum of the areas of the two shapes that it consists of. This is to say, the area of pentagon ABCDE in total will be equal to the area of the green right triangle EDC plus the area of quadrilateral ABCE. So, according to our definition, the area of this green triangle EDC equals to Z, so substitute the area of triangle EDC by Z plus this is quadrilateral ABCE. So in total, we found out that the area of the big pentagon ABCD equals to Z plus the area of quadrilateral ABCE. But we already found out that the area of quadrilateral that Z plus the area of quadrilateral ABCE equals to 1. So here, Z plus the area of quadrilateral ABC equals to 1. And from this long equation, we derive that the area of pentagon ABCD equals to 1. So now we found out that the area of pentagon ABCDE is equal to 1 square inch in its size. And that is the answer to the first question. In the next step, I present you the second question, the answer of the second question of this lecture. In the second question, our task is to find out the area of this ring shape. So, in the drawing, we have a circle, and we know that AB is the diameter of this circle, so I will down AB is the diameter of the circle, according to what is given as the question. In addition, we know that AEP equals to 9 units in its length, BQ equals to 4 units in its length, and this is again APQ, this is right angle, this is again PQM, this is also right angle. Again, our task is to find out the area of this ring shape. The ring shape is actually triangle A and B, so we have to find out the area of the green triangle A and B. So first of all, we can implement the rule 7. Okay, quickly rule 7. Only to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its side. The line we have a circle. AB is the diameter of the circle. This is peripheral angle ACB. It subtends on chord AB. This is the diameter of the circle, and therefore, according to this rule 7, peripheral angle ACB equals to 90 degrees in its size. So if we implement rule 7 in our drawing, in our drawing we have, this is peripheral angle A and B. Peripheral angle A and B subtend on chord AB. This is the diameter of the circle, and therefore, according to rule 7, peripheral angle A and B must be equal to 90 degrees in its size. In the next step, we define angle PAM. This angle is alpha. So in the right triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. It is the sum of the angles in a triangle. It is given as the question that PQ is a straight line. And according to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? We have this angle, this is 90 degrees minus alpha, plus this is a right angle, plus this missing angle, the left angle BMQ, total must be equal to 180 degrees according to rule 3. So, we found out that 90 degrees minus alpha plus 90 degrees plus this missing angle BMQ total must be equal to 180 degrees according to rule 3. And again, the sum of the angles on the upper side of the straight line PQ at point M must be equal to 180 degrees, that is to say 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ, total must be equal to 180 degrees. So 90 degrees plus 90 degrees, it is 180 degrees. 180 degrees minus alpha plus the missing angle BMQ. In total, it must be equal to 180 degrees according to rule 3. Here we have 180 degrees on both sides of the equation, so 180 degrees will get cancelled. And we left only with minus alpha plus the missing angle BMQ is equal to 0. Here we add alpha to the equation and we get that the missing angle BMQ equals to alpha. Okay, this is the missing angle BMQ that equals to alpha degrees in its side. So in the small right side BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle is equal to 180 degrees, 90 degrees minus alpha, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. Here 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. It is easy to see from the drawing that the big right triangle APM is similar to this small right triangle BMQ according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the fingers of this right triangle APM corresponding equal to all the fingers of this right triangle BMQ, therefore those two right triangles similar to each other according to angle similarity rules. So if you found out that the big right triangle APM is similar, this is the sign of similar to this small right triangle BMQ, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of the small right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle AMP over PQ of the big right triangle BMQ. AP equals to 9. Over MQ. MQ is the missing side, so we'll leave this it is. And it is equal to PM. PM is the missing side, so we leave it as it is. Over BQ. BQ equals to 4 units in its length. So in total, we have found out that (9) over QM equals to PM over 4. Here we cross multiply this equation. And we get that 9 times 4 is 36. So 36 equals to MQ times PM. And again, if you want to know that QM times PM equals to 36. In the next step, we will define the center of this circle. This point is point O. Therefore, OA is the radius of the circle that we define as R. Likewise, OB is also the radius of the circle that is equal to R. In the next step, we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equal to R. So the radius OM that is equal to R, the radius OM is 1 to point M, that is the point of tendency of tangent PQ with this circle. And now your radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, this angle also equals to 90 degrees. In the next step, we will do a construction. That is to say, from point O, we will go perpendicular on AP. Again, from point O, that is the center of the circle, we will go perpendicular on AP. Actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP. This point is point L. When doing this construction, we can do quadrilateral LOMP. In quadrilateral LOMP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 again, in total the must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. 60 degrees, and therefore this 4 again must be equal to 90 degrees in its size. So inside quadrilateral LOMP we have 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must be at a right angle not a square. So that quadrilateral LOMP is a right angle because it has 4 right angles. Write it down. This is quadrilateral LOMP, that is a right angle according to rule 5. In the next step, we will do another construction. That is to say, from point B, we will go perpendicular on the radius OM. Again, from point B, we will go perpendicular on the radius OM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. By doing this construction, we're going to do the small quadrilateral SBQM. This quadrilateral SBQM, we have 1, 2, 3 rectangles. And therefore, this fourth missing angle must be equal to 90 degrees in its size. Therefore, we can relate to quadrilateral SBQM as a rectangle because it has 4 right angles. So, as you know, this fourth quadrilateral SBQM is a rectangle. We know that the opposite sides of a rectangle are parallel to each other. Again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. If a part of a straight line is parallel to another straight line, then the straight line AP itself must be also parallel to OM. Therefore, AP is parallel to OM. So as you know, AP is parallel to OM. So in the next step, we'll copy those two parallel lines, AP and OM in your page, and also the radius AOB that cuts them. Okay. So if we copy the two parallel lines AP and OM, this is the radius AOB that cuts the two parallel lines AP and OM. Those two angles are defined as corresponding angles and are located between the parallel lines AP and OM, and therefore they are equal to each other and their sizes according to Rule 50. So repeat quickly on Rule 50. According to Rule 50, corresponding angles between parallel lines are equal to each other. So in the drawing we have line A that is parallel to line B. The red line C cuts those two parallel lines at those 2 points. In addition, we have those two angles alpha and beta that are defined as corresponding angles, and because of the fact that those two corresponding angles are located between the parallel lines A and B, they must be equal to each other in their sizes. That is to say, alpha equals to beta. So here we can implement Rule 50 because of the fact that we have those two corresponding angles that are located between the parallel lines AP and OM, and therefore they are equal to each other in their sizes. So actually, angle PAO is equal to angle MOB according to Rule 50. So if we define this angle as beta, then this angle must be also equal to beta because they are equal to each other according to Rule 50. So if you found out that angle PAO equals to beta and angle MOB also equals to beta. This is the big angle PAO that equals to beta. And this is angle MOB that also equals to beta. In the next step, I'll copy those two right triangles ALO and triangle OSB in the new page, and we prove that those two right triangles can go into each other according to angle side angle rule. But before that, in the right triangle ALO, this angle equals to beta. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in this right triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this right angle must be equal to 90 degrees minus beta, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Okay, those are the two right green triangles that are going from the original drawing. So why those two right triangles can go into each other? First of all, those two angles are both equal to beta, and therefore they are equal to each other. So this is angle LAO, and that's angle LAO. And it is equal to this angle, this is actually angle SOB. In the right triangle SOB, they are both equal to beta, and therefore they are equal to each other. AO equals to OB equals to R. They are both the radius of the circle, is equals to R. So AO equals to R, and OB equals to R. So AO, and that ALO, is equal to OB, and that OSB. They are both equal, they are both the radius of the circle, that equals to R, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So here this is angle AOL, in the right triangle ALO. And if which is equal to this angle, this is the angle OBS. In the right triangle OSB. They are both equal to 90 degrees one side, and therefore they are equal to each other. So if we prove that those two right triangles can go into each other according to angle side angle rule. That is to say, if we prove that those two angles and the side that is included between those two angles, that is R, this right triangle A and O are corresponding equal to those two angles, and the side that is included between those two angles, that is R, in the right triangle OSB. And therefore, if we prove that those two right triangles are similar to each other according to angle side angle rule. So, as you know, if we found out that the right triangle ALO congruent, this is the sign of congruent to the right triangle OSB according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that OL equals to SB. Again, from the fact that those two right triangles can go into each other, we derive that OL equals to SB. OL equals to SB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides, that is to say OL and SB, must be also equal to each other in their lengths. So, as you know, if you found out that side OL of the right triangle ALO is equal to side SB of the right triangle OSB. And again, if you found out that OL equals to SB. This is side OL, that is equal to side SB. So if we define the length of side OL as X, then the length of side SB must be also equal to X because they are equal to each other. But we also know that the opposite sides of the rectangle are equal to each other. So in the big rectangle LOMP, side LO must be equal to the opposite side PM. But LO is X, therefore the opposite side PM must be also equal to X units in its length. Likewise, in the small right rectangle SBQM, we already found out that this quadrant SBQM is rectangle. So in rectangle SBQM, side SB must be equal to the opposite side MQ. But SB is X, therefore the opposite side MB must be also equal to X units in its length. We have already found out that (36) equals to MQ times PM, or QM times PM equals to 36. Yeah, so we found out that QM times PM equals to 36. QM is X times PM. PM is also X. So we found out that X times X equals to 36. X times X is X squared, so X squared equals to 36. Here we take out all those equations and finally get that X equals to the square root of 36, that is 6. PM that equals to X is equals to 6 units in its length. M cubed is also equal to x, it's equal to 6 units in its length. In the next step, we will implement the Pythagoras theorem in this small right triangle MBQ. So according to the right triangle MBQ in the new pageant, we will implement on it the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a abbreviation for Pythagoras theorem. So here, this is the right triangle QBM that I go from the original drawing. This right triangle QBM, BM squared, that is the square of the hypotenuse, equals to BQ squared plus QM squared. So write it down. BM squared, that is the square of the hypotenuse, equals to BQ squared plus MQ squared. BM is the missing side, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, it is 16. Plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So in total, BM squared equals to 16 plus 36, that is 52. So BM squared equals to 52. Here we take a root out of this equation, and from here that BM, the missing side, the missing hypotenuse BM is equals to the square root of 52. This is side BM is equals to the square root of 52 units in its length. In the next step, I'll copy this right triangle APM in a new page and we implement on this right big triangle APM the Pythagoras theorem. Okay, this is the right triangle APM that I copied from the original drawing. This right triangle APM, according to the Pythagoras theorem, AM squared, this is the square of the hypotenuse, equals to AP squared plus PM squared. So write it down. AM squared, that is the square of the hypotenuse, is equal to AP square plus PM square. The hypotenuse AM is the missing side, so we leave it as it is, so it is AM square equals to AP square. AP is 9, therefore AP square is 9 squared, that is 81, plus PM square. PM is 6, therefore PM squared is 6 squared, that is 36. So in total we found out that AM square equals to 81 plus 36. 81 plus 36, 81 plus 36 is 117. So in total we found out that AM square equals to 117. Here we take a look out of this equation and find again that the missing hypotenuse AM is equal to the square root of 117 units in Islam. Our task is to find out the area of this green shape. The green shape is actually the right triangle A and B. So we find out the area of that right triangle A and B according to the formula that says that the area of right triangle equals to the base of the triangle times the height over 2. So the area of triangle, the right triangle A and B will be equal to the base MB times the height AM over 2. Again, the area of this height A and B is equal to the base MB times the height AM over 2. MB equals to the square root of 52 times AM. AM, we found out that AM equals to the square root of 117. Units in its name. Over 2. In total, we found out that the area of this green right triangle A and B is equal to the square root of 52 times the square root of 117 over 2. We have the algebraic identity that says that the square root of A times the square root of B is equal to the square root of A times B. So use this trigonometric algebraic identity in order to find out what is the value of the square root of 52 times the square root of 117. Actually it will be equal to the square root of 52 times 117 divided by 2. 52 times 117 is equal to 6084 divided by 2. The square root of 684 is 78 over 2. 78 over 2 is 39. So if you found out that the area of this green right triangle A and B is equal to 39 square units in size. But the green right triangle A and B, it is actually the green shape that it's the area that we are looking for. So the area of the green shape in total will be equal to 39 square units in its size. That is the answer to the second question. Okay, again we should find out that the area that we are looking for in this question, that is the area of this green shape, is equal to 39 square units in its size. So we finished with the second question. In the next step, I will summarize the lecture. I will start with the first question, of course. In the first question, our task is to find out where of this big pentagon ABCDE. So what is a pentagon? A pentagon is a closed flat shape with five straight sides and 5 interior angles. Repeat again. A pentagon is a closed flat shape with 5 straight sides and 5 interior angles. This is pentagon ABCD. Pentagon ABCDE consists of 4 sides. 1, 2, 3, 4, 5 and 5 interior angles. 1, 2, 3, 4, 5. So our task is to find out the of this pentagon ABCDE. So first of all, we join points A and B together by a straight line, and we join points A and C together, E and C together by a straight line. In the next step, we extended side VA of pentagon ABCDE by a straight line in such a way that the extended side AM will be equal to X units in this step. So AM equals to X according to our construction. When you extend a straight line by a straight line, the result BM is a straight line. So BM is a straight line. If you focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle that is right angle plus this missing angle. In total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we join points E and M together by a straight line. By joining points E and M, we get the right triangle EMA. This is the right triangle EMA. So in the next step, we prove that those two right green triangles can go into each other according to side angle side rule. So according to those two right triangles, this is right triangle EDC. So according to those two right green triangles in the equation, we prove that those two right green triangles can go into each other according to side angle side rule. So actually, those are the two right green triangles that are coming from the original drawing. So while those two right triangles can go into each other. First of all, those two sides are both equal to X and therefore they are equal to each other. That is to say, AEM equals to CD by ECD. They are both equal to X and therefore they are equal to each other. AM equals to CD equals to X. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. That is to say, angle CAM and triangle EAM is equal to angle EDC and triangle EDC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, side EA of the right triangle EAM is equal to side ED of this right triangle ECD. They are both equal to 1 and therefore they are equal to each other. So we actually prove that those two right triangles can go into each other according to side angle side rule. So that is to say, we have those two sides, and the angle that is included between those two sides in the right triangle EAM are correspondingly equal to those two sides, and the angle that is included between those two sides in the right triangle EDC. And therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, first of all, we learn that they have also the same areas. What about any triangles that can go into each other? They must have also the same areas. So we learn actually that the area of this right triangle EAM is equal to the area of this right triangle EDC. So if we define the area of this triangle EAM as Z, then the area of this triangle EDC must be also equal to Z because they are equal to each other. In addition, from the fact that those two right triangles can go into each other, we derive that EM equals to EC. EM equals to EC according to the rule that corresponding sides of congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides EM and EC must be also equal to each other on their lengths. So here side EM is equal to side EC. Side EM equals to side EC. This is side EC is equal to side EM. This is side EM. So side EM equals to side EC. In the next step, we calculated the length of line segment MB. From the drawing, it is very easy to see that MB in total equals to MA plus AB. Again, MB equals to AM plus AB. So MB equals to MA, that is X, plus AB, that is 1 minus X. So in total, MB equals to X plus 1 minus X. X minus X is 0, so we're left only with 1. So in total, we found out that to MB equals to 1 unit in its length. In the next step, we prove that this triangle MEB is congruent to this triangle BEC according to side rule. All that those two triangles congruent to each other according to side rule. So according to those two triangles in the equation, we prove that those two triangles MEB and EBC congruent to each other according to side rule. Machine, those are the two triangles that are going from the original drawing. This is triangle EMB, this is triangle EBC. So what those two triangles can go into each other? First of all, EM equals to EC. EM equals to EC, according to what we already found out. In addition, we have MB is equals to VC equals to 1. They are both equal to 1, therefore they are equal to each other. And finally, EB is the common side that belongs to both triangles. This is side EB, that is the common side that belongs to both triangles. So if we found out that triangle EMB can go to triangle EBC according to side rule. And from the fact that those two triangles can go into each other, we derive that they have also the same areas. That is to say, the area of this triangle EMB is equal to the area of this triangle EBC. Again, the area of triangle EMB is equal to the area of triangle EBC because they can go into each other. So in the next step, we calculated the area of triangle EMB. So what is the area of triangle EMB? It is equal to the base MB times the height AE over 2. And again, the area of this triangle MEB in total is equal to the base BM times the height AE over 2. BM or MB equals to 1, AE also equals to 1. So BM times AE is 1 times 1, that is 1. So, and we have to divide it by 2. So in total, EB equals to 1 half. So you can write here that EB equals to 1 half, and from this equation, 1 half equals to the area of triangle EB equals to the area of triangle EBC. We derive that the area of triangle EBC will be also equal to 1 half. Okay. So therefore, the area of triangle EMB plus the area of triangle EBC in total it will be equal to 1 half plus 1 half, that is 1. So in total, we found out that the sum of the areas of those two triangles in total it is equal to 1 square in its size. But quadrilateral EMBC consists of those two triangles. Again, quadrilateral EMBC consists exactly those two triangles, and therefore the area of quadrilateral EMBC, the big quadrilateral EMBC, must be equal to 1 because it consists of those two triangles. Again, we found out that the area of the big quadrilateral EMBC is equal to 1, but quadrilateral This is the big quadrilateral EMBC. It also consists this green triangle EMB and this quadrilateral EMBC. And the area of quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, must be equal to the area of this right green triangle EMB, EMA, plus the area of this quadrilateral ABCE. Repeat again. The area of quadrilateral EMBC, that is 1, must be equal to the sum of the areas of the two shapes that it consists of. The two shapes that it consists of is quadrilateral, the right green triangle EMA plus the area of quadrilateral ABCE. So the sum of the areas of the two shapes that it consists of must be equal to the area of quadrilateral EMBC, that is 1. So if you found in total the area of the green triangle EMA plus the area of quadrilateral ABCE equals to 1. But the area of triangle EMA is equal to Z according to our definition. So you can substitute the area of triangle EMA by Z and get that Z plus the area of triangle ABCE equals to 1. Repeat again, Z plus the area of this quadrilateral ABCE equals to 1. Our task is to find out the area of this big pentagon ABCDE. So what is the area of the big pentagon ABCDE? Actually, for the drawing it is very easy to see that pentagon ABCDE consists of two shapes. It consists of this ring right triangle EDC and it consists also this quadrilateral ABC, and therefore the area of pentagon ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of the big pentagon ABCD must be equal to the area of the green right triangle EDC plus the area of quadrilateral ABC. But according to our definition, the area of the green triangle EDC is Z. So we can substitute the area of triangle EDC by Z. So in total we get that the area of pentagon ABCD equals to Z plus the area of quadrilateral ABCE. But we have already found out that Z plus the area of quadrilateral ABCE is equal to 1. So we can write here that Z plus the area of quadrilateral ABC equals to 1. And from this log equation, we will derive that the area of the big pentagon ABCD equals to 1. Okay, again, the area of the big pentagon ABCD equals to 1. So, the area of this big pentagon ABCD equals to 1 squared in its size. So, finish with the first question. In the next step, I presented to you the second question and we solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. It is given us the question that in the drawing we have a circle, and we know that AB is the diameter of this circle. In addition, we know that BQ equals to 4 and 9/7 AP equals to 9. And our task is to find out the area of this green shape. So first of all, we can implement here rule 7. According to rule 7, if a peripheral angle is subset of the diameter of the circle, it must be equal to 90 degrees in its size. This is peripheral angle AMB. This is peripheral angle AMB. That's subset of code AB. This is the diameter of the circle according to what is given in the question. Therefore, according to rule 7, peripheral angle AMB must be equal to 90 degrees in its size. In the next step, we define this angle and get PAM as alpha. So the right triangle APM, this angle equals to alpha, This angle equals to 90 degrees, and therefore this missing angle must equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. It is given as the question that PQ is a straight line. So if we focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to all three. All three says that the sum of the angles one side of the straight line is equal to 180 degrees. So which angles we have the upper side of the straight line PQ at point M? We have this angle that is 90 degrees minus alpha, plus this angle is 90 degrees, plus this missing angle in total must be equal to 180 degrees according to all three. So 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ in total must be equal to 180 degrees according to all three. 90 degrees plus 90 degrees is 180 degrees, so in total in this side of the equation we have 180 degrees minus alpha plus the missing angle BMQ in total must be equal to 180 degrees. Here we have 180 degrees from both sides of the equation, 180 degrees will get cancelled, and left only minus alpha plus the missing angle BMQ in total it is equal to 0. Here we add alpha to this equation, and we found out that the missing angle BMQ equals to alpha. This is the missing angle BMQ that is equal to alpha. From the drawing, it is very easy to see that the big triangle APM is similar to this small triangle BMQ according to angle similar to. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and therefore they are equal to each other. So we found out that all the angles of this big right triangle APM are corresponding equal to all the angles of this right triangle BMQ. Therefore, similar to each other according to angle similar to. And from the fact that those two right triangles are similar to each other, we know that the following relationship exists between their sides. We write that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of this small right triangle BMQ. And again, we write that AP over MQ equals to PM over BQ. AP is 9 over MQ. MQ is the missing side, so it is, and it is equal to PM. PM is also the missing side, so it is, over BQ. BQ is 4. So total, remember that 9 over MQ equals to PM over 4. Here, because multiply this equation, and find out that MQ times PM equals to 9 times 4, that is 36. And 36 equals to MQ times PM. In the next step, we define the center of this circle, this point as point O. So OA is the radius of the circle that is equal to R according to our definition. OB is also the radius of the circle that is equal to R. In the next step, we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equal to R. The radius of M is equal to R, the radius of M is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to all one. In the next step, we did a construction, that is to say, from point O, that is the center of this circle, we draw perpendicular on AP. Again, from point O, we draw perpendicular on AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We find the touching point of the perpendicular from point O and AP. This point is point M. By doing this construction, we can do quadrilateral NO and P. Quadrilateral NO and P, we have 1, 2, 3 angles. The sum of right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, so that must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth integral must be equal to 90 degrees and inside. So inside quadrangle LOMP we have 4 integrals, and therefore according to rule 5, quadrangle LOMP is a rectangle. Because it has 4 integrals. Likewise, we did another construction, that is to say from point B we draw perpendicular on the radius OM. Again from point B we draw perpendicular on the radius OM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to construction. We define the touching point of the perpendicular from point O and OM. This point is point S. By doing this construction, create quadrangle SBQM. In quadrangle SBQM we have 1, 2, 3 rectangles, and therefore this fourth angle must be equal to 90 degrees inside. Therefore quadrangle SBQM is a rectangle according to rule 5. In the next step, actually we know that the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LO is parallel to the opposite side OM. But again, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. Again, LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line AP also, the straight line AP itself must be also parallel to OM. So if you found out that AP is parallel to OM. In the next step, I copy those two parallelize AP and OM in the new page. Also the radius EOB that cuts them. So this is side AP that is parallel to side OM, and this is the radius AOB. So those two angles are defined as corresponding angles, and are located between the parallel lines AP and OM, and therefore they are equal to each other and their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta according to rule 50. So this is angle PAO, this is equal to beta, and this is angle MOB, this is also equal to beta. In the next step, I copied those two right triangles in a new page, and we prove that those two right triangles can go into each other according to angle side angle rule. So those are the two right triangles that are going from the original drawing. So when those two right triangles can go into each other. First of all, we know that those two angles are both equal to beta, therefore they are equal to each other. So angle LAO in the right triangle ALO is equal to angle SOB in the right triangle SOB. They are both equal to beta, therefore they are equal to each other. In addition, AO equals to OB. AO equals to OB, they are both the radii of the circle, that equals to R, therefore they are equal to each other. AO equals to OB equals to R. And finally, those two angles are both equal to 90 degrees once beta, and therefore they are equal to each other. So if you wonder that angle AOL in the right triangle AOL is equal to angle BOS in the right triangle BOS. They are both equal to 90 degrees once alpha, and therefore they are equal to each other. So if you prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we prove that those two angles, and the side that is included between those two angles, in the right triangle ALO corresponding equal to those two angles, and the side that is included between those two angles in the right triangle OSB. And therefore those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that LO equals to SB. Again, LO equals to SB according to the rule that corresponding sides that can go into triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides LO and SB must be also equal to each other in their lengths. So if we define the length of side LO as X, then SB must be also equal to X because they are equal to each other. Then OL equals to SB. This is side LO, this equals to SB. So if you define the length of side LO as X, then SB must be also equal to X because they are equal to each other. But we know that the opposite sides of a rectangle are equal to each other. So in the big rectangle LO and P side LO must be equal to the opposite side PM. But LO is x, therefore the opposite side PM must be also equal to x unit in its length. Likewise, according to the symbol, in the rectangle SBQM, side SB must be equal to the opposite side MQ, but SB is x, therefore the opposite side MQ must be also equal to x units in its length. We already found out that MQ times PM equals to 36. MQ is x and PM is x. QM is x and PM is x. So in total we found out that x times x equals to 36. So x times x is x squared, that is equals to 36. Here to go out of this equation, I found out that x equals to the square root of 36, that is 6. So x equals to 6 and x equals to 6. The next step, I copied the right triangle BQM in an equation, implemented this right triangle BQM, the Pythagoras theorem. This is the right triangle BQM that are coming from the original drawing. In this triangle BQM, the right triangle BQM, BM squared, that is the square of the hypotenuse, equals to BQ squared plus QM squared. BM is the missing side, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16. Plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So in total, if you want to know that BM squared equals to 16 plus 36, that is 52. So BM squared equals to 32. Here we to go out of the equation, if I found out that BM equals to the square root of 52 units in its length. This is side BM, that is equals to the square root of 52 units in its length. Likewise, I copied this right triangle APM in an equation and implemented on this big right triangle APM, the Pythagoras theorem. This is right triangle APM, that is coming from the original drawing. AP equals to 9, PM equals to 6. AM, therefore AM is the missing side. So according to the Pythagoras theorem, AM squared, that is the square of the hypotenuse, equals to AP squared plus BM squared. And again, AM squared equals to AP squared plus BM squared. AM is the missing side, so limit is this, so it is AM squared equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81. Plus BM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, if you found out that AM squared equals to 81 plus 36, that is 117. So AM squared equals to 117. Here we to go down to this equation, if we found out that the missing according to AM, it is equal to the square root of 117 units in its length. This is side AM is equal to the square root of 117 units in its length. The green shape, it is actually the right triangle AMP. So we have to find out the right triangle AMP. According to, you know that there any triangle equals to the base of the triangle times the height over 2. The base is MB, the height is MA divided by 2. So there are the right triangle MB AMB is equal to the base MB times the height AM over 2. MB is equal to 52. And AM is square root of 117. And MB is the square root of 52, and MA is the square root of 117. So in total, if you found out that they have the right triangle AB equals to the square root of 52 times the square root of 117 over 2. We have the algebraic identity that says that the square root of A times the square root of B is equal to the square root of AB. According to this algebraic identity, we get that the square root of 52 times the square root of 117 equals to the square root of 52 times 117. So here it is divided by 2. 52 times 117 is 6,084. So inside the root we have 684. The square root of 684 is 78. So in total, the green shape equals to 78 over 2, that is 39. So in total, if you found out that the area of the green shape equals to 39 square inches inside. So repeat again, if you found out that the area of this green shape is the area that we are looking for in this equation, it is equal to 39 square inches inside. Okay, thank you very much.